Welcome back to Chapter 1.3, Part 3 of 11. In Part 2, we define bias as where a recipe sits, on average, across all possible samples. Now we put the sample mean on trial. We prove it is unbiased for any sample size, draw a surprising lesson about data, and then meet a recipe that quietly aims low, and see exactly which assumption makes the proof work. Let us prove it. Suppose each claim, x sub I, is drawn from a population with mean mu. Using only that expectation is linear. It passes through sums and constants, which we established in Chapter 1.2. The expectation of x bar equals the expectation of 1 over n times the sum of the x sub I. Pull the 1 over n out front, and it becomes 1 over n times the sum of the expectations. Each expectation is mu, so we have 1 over n times the sum of n copies of mu, which is 1 over n times n mu, which is just mu. The sample mean is unbiased, full stop, for any sample size, even n equals 3. That is a strong and slightly surprising fact. Unbiasedness has nothing to do with having lots of data. A 3-claim average is just as unbiased as a 3 million claim average. What changes with n is something else entirely, the variance, which is the heart of the chapter and comes shortly. Now contrast with a biased recipe. Suppose Priya, worried about a budget meeting, quietly drops the 3 biggest claims before averaging to remove outliers. The recipe now systematically discards the right tail of a distribution that is skewed right. A few catastrophic fires, lots of small claims, the way insurance losses almost always look. Across all possible samples, this recipe lands below mu on average. It is biased downward. That bias is not a mistake she made on Tuesday. It is baked into the recipe and would persist no matter how much data she collected. And here is the deeper lesson. The unbiasedness proof used exactly one thing, that the expectation of every claim equals mu, that all 200 claims are drawn from the same population whose mean Priya cares about. If her spreadsheet over represents one high-risk county, because that county's broker files more diligently, then the claims are not all draws from the target population. The expectation no longer equals mu, and the proof collapses. The math did not break, the assumption did. Estimators are only as good as the sampling assumption behind them. To summarize Part 3, the sample mean is unbiased for any sample size, even 3 claims, because expectation is linear and every claim has mean mu. Unbiasedness has nothing to do with how much data you hold. The whole proof rests on one assumption, that every observation is drawn from the target population. Drop the 3 biggest claims or oversample one county, and the assumption breaks and the proof collapses. The first thing to interrogate when a number looks wrong is whether the data you fed the recipe actually came from the population you meant to study. But aiming true on average is only half the story. In Part 4, we measure how jumpy the recipe is from sample to sample, the variance.